Let's continue talking about how we can simplify expressions using the rules for exponents. We've got some warm-up problems here. There's basically a statement or a definition, and then we've got an example that applies that statement. So let's talk about separable fractions, or how we can separate fractions. So what happens there is if we've got an expression like this, each term, and this is important, each term in the numerator, in other words on the top, can be written separately over the denominator. Okay, and denominator is just a fancy word for the bottom. So we're going to take each one of the terms in the top and write it over the bottom. So here we would have 4x squared over 2, and then the sign's important, so minus 6 over 2. So what we end up with on that one is we've got, let's simplify this one. We can cancel the 4 and the 2, so that's going to be a 2x squared, and then minus 6 over 2 would be a 3, so that would be our answer there. I'm going to go ahead and circle that one. And then we've got bases, exponents, coefficients, and constants. So it says label each part of the expression as a base, a coefficient, or a constant. Now remember, a constant is just a plain old number. It's just sitting out there. It's not attached to anything, just a plain old number. So what we've got right here is that is the coefficient. So I'm just going to write co-EFF for that. This one is the base. All right. That, of course, is written smaller in superscript, so that one is the exponent, so I'll just write exp. And this, of course, is the constant, okay? Plain old number just hanging out at the end there. And then like terms. Again, let's talk about like terms. Like terms have the same variables and the same exponents. Now, you know what like terms are. We use these all the time, and this is a typical way of explaining this, but we'll see that there are some other ways to think about this. So when we've got 4x plus 3x squared plus 5x, all of these terms have an x in them, and remember, terms are separated by plus and minus signs, addition and subtraction. So they've all got an x, but these two have the same exponent. So we're going to put the two of those together. So I'm going to go ahead and write this in the correct order. I'm going to write this in descending order. So I've got that one taken care of. And then we've got 4x plus 5x. We end up with 9x. Now there's nothing terribly taxing about this one. This is a pretty easy one. You've seen stuff like this before. But we want to be able to use these properties and these ideas and maybe settings that look a little bit unfamiliar. So we're going to come down here and we're going to use what we know about greatest common factors, GCFs, like terms and properties of exponents to simplify expressions that are a bit more complicated than the ones that we've seen before. So this is example 2. You'll notice that we've got this fraction where we've got a couple of different terms on the top and then one single factor on the bottom. Sorry, a product made up of two factors, A and B. Now remember, when we're working with division, we cannot cancel terms, we can only cancel factors. So let me tell you what I mean by that. When we're doing a problem like this one right here, a lot of people would be tempted to say, oh, I can cancel this AB with one of those A's and B's right there, and then we're all set to go. That would be canceling factors with a term. This 8a squared b is a term, and so is 3a squared b. So we have to do this a little bit different. So here's what we're going to do on this one. What we're going to do is we're going to look for a common factor on the top. So we're going to pull out a factor so that we can see what we can cancel off. So we take a look at that top right there, that numerator, and we notice that we don't have any numbers in common, but I do have an a squared and a b here, and I've got an a and a b here. So they at least both have an a and a b. So I'm going to write down an ab here. And then what's left is I've got the 8. I didn't touch that at all. We took out one of the a's, so that would mean there would be an a left. And we took out the b, so there's no b left. And then we've got a 3, okay? And we took out the a, so that one's gone. And we took out one of the b's, so there's one b left. So this is what we've got there. So this would be ab. And we can cancel this factor, a times b, with that factor of a times b. So we end up with 8a plus 3b. Now, this is a really important idea. I'm going to go ahead and put a star by this. Please make sure you're looking to cancel factors. Please don't cancel terms. And this next one might illustrate that a little bit more because we've got maybe easier numbers to recognize. So a lot of people would look at this and say, hey, gosh, I can cancel this 2 with that 4. We do stuff like that all the time, or maybe the 2 with the 18. We would be canceling a factor with part of a term, and that's not okay. All right, so what we look for here is we look to say, hey, what can we take out? So let's look for a GCF right here, so practice those skills. So I'm going to take out, let's see, we've got a t cubed, we've got a t squared, and we've got a t. We can definitely take out a t. We can't take out any numbers because this has 2's, this has 2's and 3's, and this just has 3's. So there aren't any numbers that we can take out there. So we're going to be left with, let's see, if I take out a t, I'm left with 4t squared. If we take out a t, we're left with plus 18t. And then if we take out a t, we're left with minus 9. And then the denominator is going to be 2t. So now I can go ahead and look and see what I can cancel as far as factors go. So let me highlight the factors here. This is a factor, and this is a factor, and that's a factor, and that's a factor. So we can cancel off any factors with on the bottom with factors on the top. So I can go ahead and cancel off this t with this t, and what I'm left with is a 4t squared plus 18t minus 9, and that would all be over 2. Now I'm going to go ahead and circle that, and again I'll just point out, we're really tempted to look at this and say, gosh, can't I cancel the 4 with the 2? You can't, because this 4 is part of a term and that 2 is a factor. So you can't cancel a term with a factor. You can only cancel factors. Okay, let's go ahead and take a look at this one. Let's go ahead and let's see. The leading one here is negative, so we're definitely going to take out a negative. And I'm going to zoom in on this one just a little bit to make this a little bit easier to see and a little bit easier to work on. So I'm going to take out a negative, and let's see, the numbers, we've got a 9, a 60, and a 3. So I'm going to go ahead and take out a 3. And then variable-wise, we've got t to the 4th, t to the 3rd, and t to the 2nd. I've got 2 t's in every one of them, so I'm going to take out a 2t squared. So let's see what's left when I take out a negative 3t squared. So number-wise, if I take out the negative, I'm left with a positive, and 9 divided by 3 would be 3. So this is going to be positive 3. And we took out 2 of the t's, so this would be t squared. Let's see, we took out the negative, so this is going to be positive, and 60 divided by 3 would be 20, so this is positive 20. We took out 2 of the t's, so there's going to be 1 t left. And then let's see, we took out a negative. That's going to automatically turn that sign to the opposite of what it was, just like we did over here. I took out the 3 and I took out the t squared. So what's left? Well, remember, there's always something left when we factor something out. In this case, there's a 1 left. And then on the bottom, we're going to have negative 3t to the 5th. So let's go ahead and cross-cancel what we can. Again, I'll highlight factors. This is a factor, that's a factor, and that's a factor. So notice what we've got here. We can go ahead and cancel off the 3's, okay, the negative 3's, and I can cancel 2 of these with 2 of those, so that means there's 3 of those left. So this is going to be 3t squared plus 20t minus 1 over, t to the 3rd. Make sure we get that right, okay? So there's the answer on that one, and again, we're really tempted to say, gosh, can't we cancel some of these t's? We can't, because we'd be canceling part of a term with a factor, and that's not okay. So let me come back here, and before we do anything else, I want to move on. Before we move on, I want to take a look at this example up here again. Very first example that we did today. Let's take a look at this. So we did it this way by separating that fraction, and we ended up with 2x squared minus 3. Now that works out totally okay on that one, and we could possibly do each one of these this way, but it's a really good skill to be able to factor something out and then cancel that factor. So that's the skill we're working on here. But let's take a look and see if we can come up with the same answer that way. So you'll notice that we've got 4x squared minus 6. They both are even, so I can take out a 2. So I'm going to go ahead and take out a 2. And when I take out a 2, I'm left with a 2. We didn't touch the x squared. When I take a 2 out of a negative 6, I'm left with a negative 3. And then, of course, we have the 2 on the bottom. Now, notice that I can cancel this 2 with that 2. So we end up with exactly the same thing. So it's good to know that it works both ways. So now let's come down here and let's take a look at something that turns out to be relatively easy, hopefully, but a lot of people struggle with this because the minute we put a variable in the exponent, it seems like things get really, really complicated. But again, if we pay attention to the details, we know what the properties are and stuff like that, that's going to make it a lot easier. So I want to show you an example. So look at this one right here. It says if 3x squared plus 7x squared is 10x squared, and I don't think anybody would argue with that. We've been doing that for a long time. It says, what does 3 times 2 to the x plus 7 times 2 to the x? What does that equal? Well, if you take a look at the structure of these two problems, they're basically exactly the same. This says 3 of these things right here, 3 of those x squareds plus 7 of those x squareds is 10 of those x squareds. Well, this is saying exactly the same thing. This is 3 2 to the x's plus 7 2 to the x's. So these have the same base and they have the same exponent. These have the same base and they have the same exponent. So we're going to end up with exactly the same type of thing. It's going to be 10 of whatever these are. Okay? Whoops, I need an x on that. Okay? So a more complete way to describe like terms is to say this. They have the same base and they have the same exponent. So a lot of times we'll just say that they've got the same variables and the same exponents, but the same is true whether the base is a variable or an exponent. And this works with more complicated things that you might run into down the road. So let's take a look at this one. It says simplify the expression. If it can't be simplified, just write simplified. So on this one, we've got 10 times 2 to the x minus 4 times 2 to the x. Or another way to think of it would be 10 of these minus 4 of these is going to be 6 of whatever these are. Okay? Now, there are times where you'll see things written this way. Occasionally, you'll see this written as 6 times 2 to the x, and the x will be in parentheses. Remember, this is just the power property at work here. We can write it either way, so either one is fine. All right, and then let's take a look at this one. We've got a constant right here. We've got a variable expression with a variable in the exponent, so we've got kind of an exponential here. Same type of thing down on this one. So again, you'll notice what we have here is those are like terms because they have the same base and the same exponent. So we're applying this idea that we wrote in this box over on the side. Now, there's no perfect way to write these. You can write these in almost any way you want. So if I have 4 of these plus 8 of these, I'd have 12 and then 3 to the x. It's 12 times 3 to the x. I'm going to go ahead and write the minus 9x, and then I'm going to write the plus 5. So this would be the simplified version of that answer. So this next one's kind of interesting. We've got 6 to the x plus 6. Now, people will look at this and go, gosh, they've both got 6's. There ought to be some way to put this together. But remember, this right here is just a constant. And if we were to put an exponent on it, it would have to have an exponent of 1. So if we look at it in terms of this description of like terms, they both have a base of 6, but this has an exponent of x, and this has an exponent of 1. So they have the same base. They have different exponents. We can't combine these. So we're going to write simplified here. Okay, so that would be the answer on that one. There's not really a good other way to write this, so we'll just go ahead and circle that and say simplified. So let's take a look at the next one. And on D, the detail that we need to catch here is that we are not combining these. So people have a tendency to look at this and say, oh, we've been combining like we did up here. This has a base of 4, this has a base of 5, so we can't do anything there. So we're not combining. What we're doing here is we are multiplying. Okay, this is a product, so we got to be careful. We apply different rules. So if you wanted to, what you could do is you could rewrite this using the commutative property of multiplication. So I'm going to go ahead and write the 2 times the 6 out here. Then that would be times 4 to the x, and then times 5 to the x. We can go ahead and multiply the 12s together, or sorry, the 2 and the 6 together and get 12. And then we've got 4 to the x times 5 to the x. Well, this is what we were talking about the other day. So what we can do here is we can kind of apply this and say, look, this is like the power property in reverse. So what we do here is we'd say, look, I can just write 4 times 5 to the x, and then this would be 12 times 20 to the x. And that would be the answer. That's how we're going to write that. So on this problem right here, we've got the same type of thing, but they do have the same base in this particular case. So let's go ahead and multiply the numbers there. So we multiply those coefficients out in front, and we get -8. And then I'm going to raise something to the x, and what it's going to be is we multiply these together, just like we multiplied the 4 times the 5. So this is going to be 25 raised to the x. So we'll go ahead and circle that, all set to go there. Now this one gets kind of interesting. Again, look at the similarity. Look how close it is to the one up above there. But again, the operation is different here, so we apply different rules. We're not combining like terms here. We're literally multiplying these together. So there are a couple different things that we could do here. They both have the same base. So remember, if we're multiplying them and they have the same base, we add the exponents. So one thing that we could do is we could write this as 6 raised to the x plus 1. Totally okay to have an expression like that in the exponent. So this right here would work just fine. Some people might like to just slide this out front and then write 6 times 6 to the x. Either one is probably okay, but this is probably a better way to write it because we're writing it with one single base. It kind of acknowledges the fact that they have the same base, so we're applying those properties of exponents. Let's come down here and take a look at the next line. On this next line, what we've got is we've got division problems, so we've got quotients on every one of these. So let's take a look at what we can do on this one. I'm going to go ahead and cancel the 7 with the 14. That's going to make this a 2. And then we're going to apply this this way. So I'm going to have a 2 out here, and then I'm going to have a 21 on the top and a 3 on the bottom. Again, kind of applying that power property in reverse. Whoops, I need to write an x right there. So now what we can do is we can write this as a 7. So this would be 7 to the x. And it's important to note what this is. This 7 would be in the numerator because the bigger base is in the numerator. And then that 2 is in the denominator, so we're going to write the 2 right there. So that right there is the answer. Let's go ahead and take a look at the next one. Again, we'll do some simplification here. We'll put a 3 on the bottom. And then on this one, you'll notice if I were to write 5 over 10 and raise that to the x, what I'd end up with is I'd end up with 1/2 raised to the x. Now, I could write it this way. So notice that we've got nothing really left on the top. So I could write a 1/3, and then we could do times 1/2 raised to the x. That would be one way to do it. Totally okay to write it that way if you want to. Or we could do this. We could write this as a 1 on the top, and then let's apply this exponent to both the top and bottom separately. So this is going to be 1 to the x, and this is going to be 2 to the x. Well, if you think about it, 1 raised to any power is going to be 1. So this is going to be 1/3, and then let's see, this would be a 1 on the top and 2 to the x on the bottom. So this would be 1, and then on the bottom, 3 times 2 to the x. Okay, and that would be okay. Either way would be fine there. And then let's take a look at this last one. And notice this one's kind of interesting because here we've got 2 to the x on top and 2 to the x on the bottom. Well, these are factors. There's no addition or subtraction here, so I can just cancel that. So those are gone, and then I end up with a 12 over 3, which of course is a 4. So the answer on that one is just 4. Now, we want to quickly review some ideas that we talked about earlier in the year. So this is function notation. F of x is 6 times 3 to the x, and g of x is 4 times 3 to the x. And we just want to go through and just remember these are operations with functions. So we're going to be adding the functions, we're going to be subtracting the functions, multiplying them, and then dividing them. And then we want to simplify them as much as possible. So this is just going to be 6 3 to the x plus 4 3 to the x. And then I end up with 10 3 to the x, and then you'll notice that sometimes I write it on the inside and sometimes on the outside. Subtracting is going to be the same thing, but we're going to have a different operation. So we're going to have 6 of these minus 4 of these, so that's going to be 2 of whatever that is, so that's 3 to the x. So there's our answer there. We're going to multiply these together, so this is going to be 6 3 to the x times 4 3 to the x. So we end up with 24, and then remember, we multiply the bases together, so this is going to be 9 to the x. All right, and then we come back here, we're going to do a division problem really quickly. F is on the top, g is on the bottom, so this is going to be 6 3 to the x over 4 3 to the x. Those are going to cancel, and we end up with, other way around, we end up with a 3 on the top, and we end up with a 2 on the bottom, so 3 over 2. Now, go ahead and circle the self-assessment. If you want to stick around for one quick thing, I would like to show you a different way to do this particular problem and this one right here. So I'm going to put a circle around this one and a circle around this one. So here's another way to do this, and this is a good thing to keep in mind, especially if you're going to do some higher mathematics. So one way to do this would be just be 24, and then I can also write it this way. If these have the same base, then we add the exponents. So watch what happens if I write it this way. I can keep the same base, and if I do x plus x, I end up with 2x. So this is just the same type of thing if I were to do x squared times x to the 4th. I'd have the same base and I add the exponents. So it's the same idea there. I get a 6 on this one. I add the exponents, x plus x, I get 2x. Now, is this the same thing as this one right here? Well, the answer to that is yes, because watch what happens if I write it like this. 24, and then I write 3 to the 2nd, and let's say I raise that to the x. This would be a power raised to a power, so I can do 3 squared, so that would be 24. 3 squared is 9, and then I can raise that to the x. So the answer to that is yes, it is. And let me quickly do this one right here. So this would be -8. And then we've got, let's see, 5 to the 2x. Now, there are times where it might be advantageous to just leave it written like that. But if you want to take the 2 and apply that, because it's a number, we can apply that number exponent. We end up with -8, and then 5 squared would be 25 raised to the x, and you'll notice it's exactly the same thing. Pretty cool that it works a lot of different ways. That's one of the nice things about math. All right, good luck on the assignment.